So let me introduce the research topics that in each individual groups. So I'll start by myself, and I'm a theorist, so I'm working on many aspects of these optical atomic systems, either bosons or fermions, or a mixture of bosons and fermions. We study the many body properties of these optical atomic systems. And so these are some pictures from Randy Hewlett's lab. He's an experimentalist working on these optical atomic systems, and he has currently has 3 experimental setups. He works on both bosons and fermions. And this is a picture of atomic condensate, and these structures. Well, this is the density profile of these atomic systems, and these structures are called solitons, which are localized objects that are not destroyed by collision. And this is another. So these are all force color density profiles, and this shows a system of 2-component Fermi gas. So we can, at low temperature, the atom goes on phase transition, becomes superfluid. So different, the Fermi atoms can couple with each other to form like Cooper pairs, like electrons in superconductors. And these are some pictures from Tom Killian's lab, and he's working on 2 main subjects. One is his favorite atom is strontium, which is an alkali earth atom. And this is the recent achievement we obtained Bose-Einstein condensation of a neutral strontium atom. And this is a picture of strontium plasma. And what we do is we create very cold strontium atoms, then we use laser light to ionize the neutral atom. So neutral atoms become an ensemble of atoms become an ensemble of ions and the electrons. So it's a plasma. But these plasmas are not the plasma that Dr. Chen just mentioned. These plasma are very cold. And this is a picture of ordinary plasmas which live above 1000 Kelvin. So ordinary, when you think about plasma, think about very high temperature stuff. But the plasma that is created in the laboratory of Dr. Killian has a temperature around below 1 Kelvin. And again, one of the beauty of studying these very, very low temperature ultra plasma is you can actually learn something of the high temperature plasmas, which are very difficult to manipulate in the laboratory. Right. This is what Dr. Dunning is doing in his lab. He's working on Rydberg atoms. So these are the very highly excited atoms. So these atoms are actually very well described by the Bohr model, which was proposed by Niels Bohr in the early days of quantum mechanics. And so by studying these highly excited Rydberg atoms, you can actually explore the boundary between classical physics and quantum physics. And we know that ultimately everything is governed by quantum mechanics, but in ordinary life, in these ordinary matters, we don't see often the quantum mechanical property of the system. So they behave like classical objects. So where do this transition come from? How quantum mechanics make a transition to classical physics? And by studying these Rydberg atoms, we may have some insights from these quantum classical boundary. And also, people have proposed to use these Rydberg atoms as a qubit that is the fundamental object for quantum information process. So you can manipulate these Rydberg atoms and to So I will stop here. These are some pictures of the people that are working in MO, and some rooms for more people. We'd like to attract the tourists. Please come to talk to us. Do your visit. Thank you.
Thank you.